Okay, in our next example of using the same state of stress we had in the two other ones here is to find not Tog max, but rather we're going to find the max normal stresses, which are called, of course, the principal stresses. So we don't call them sigma max anymore. We are clever and we call them sigma 1 and sigma 2, where sigma 1 is defined to be the algebraically largest principal stress, and sigma 2 is to be the smallest. Not absolute value, but the algebraic values. Right? So first step is to define what our state of stress is and identify the normal stress on the two orthogonal planes and the accompanying shear stress. And that we've done that before. That's the minus 1400 for X, positive 1000 or tension for Y, and the minus 500 for the shear stress. Then we go and we find the stress equation that gives us the principals, or the largest ones, right? And we're just going to substitute those values in. Now, when we do this, keep in mind, we got to, again, be very careful and have the correct sign, plus and minus, associated with those values, right? Got to have that. Note, though, in the big picture here, we get this square root term that is got something squared plus another something squared. That turns out to be just like the Pythagorean theorem. We've got one leg of a triangle squared plus another leg of a triangle squared, and then we take the square root of that. Then notice that there's a plus or minus value that's associated with this, so that when we go and get our maximums, our principal values, that we really get two answers that come out of this equation. So this first term is really the average of the sigma x and sigma y, including their signs. So minus 1400 plus the 1000 is a minus 400 divided by 2. That's where the minus 200 comes from. Put all those things into here, and this hypotenuse value, or what you'll eventually learn to think of as a radius value, is 1300. So we're going to get two values that come out of this. One's 1100, and it's a positive 1. That's the 1300 minus the 200. And the other is the negative 1500, which is the minus 1300 and 200. Those are our two numerical values for our principal stresses. One is going to be in tension, that's the positive 1. One's going to be in compression, that's the negative 1. Make sure you put the actual numbers into this equation and you get exactly those same values. That's when you know you're beginning to really understand how to manipulate the equation correctly. Then from there, we got to figure out how those are all oriented and put everything on the stress block. So we're going to find what the angles are to those two particular locations, right? So that expression is tangent 2 theta p is equal to this thing over here. You're probably not going to remember all that. What you want to remember is that, once again, there's a triangle thing going on right here. It's a rise over run business. And it turns out that to the principal planes, it's going to be tau xy, this one over that one. That's what's this setting up. When we did the maximum shear stress, it was the reciprocal of that. So that was the rise, that was the run, and there was also a negative sign that got put out there in front of that one, right? But this one is set up this way, and we put those numbers in there, and what you're going to find that that's 11.31 degrees is probably the answer your calculator or whatever tool you're using is going to give you. But there's more than one answer to this expression, right? And they're going to turn out to be at 90 degrees apart, really 180 here, but then you divide by the 2, and they're going to be 90 degrees apart. So that's why you see 11.31 and a minus 78.69 degrees. And you got to figure out which one of those angles is associated with each one of those. And it's not the plus or minus associated with that. That has nothing to really directly to do with it. When you know Morse circle, this will become really easy to do. When you don't, here's what you're left with having to do. You have to go back to your basic stress equations for any arbitrary plane, put in your new theta value, say 11.31 degrees, put it all in there, and figure out which one goes with which. And that's how I came about this stress block that you see here, rotated slightly, and with the compression here on the mostly vertical plane, and then the tension on the other one. Right, now here's a quality control check that you can kind of help with. Right, notice back over here in the original state of stress that was given to us. Right, we've got this vertical direction has the 1000 in tension. and the other direction is the squeezing. And you got this 1500 that wants to, or sorry, 500 shear stresses that want to pull and create a tension going in that direction. The combination of that and this 1000 is what gets us to this sort of up to the left slightly, that's the 1100, and that the other one, which has a big 1400 squeezing, that's in this opposite direction of how that shear stress block is our shear stresses are trying to deal or deform that block. And that sort of hints at why we're in that direction on those planes. That's a hand waving argument, though again, the way you prove it coming out of the equations are you have to take the equations and back substitute into these equations to get there. That's long and that's tedious. More circle will make this way easier. Now, you also don't see any shear stresses on here, and that's because by definition, right, we can prove this, on the principal planes, the shear stress is 0. How do I know this? Well, I've gone through this before, and again, what you do is you take any one of those principal angles and you put it into that shear stress equation here, and you'll find out you get 0. You can also do that symbolically, and you'll prove that they must be 0 on those planes. Right? There's a lot of work to do there, and sometimes that's sort of clever shortcuts. In this case, it's really not that clever. It's sort of a direct thing. You just have to not substitute in for angles, but substitute in for bigger, larger quantities, and it'll make that derivation or that proof a little bit easier to do. Okay, so let's back up again. When you're finding these principal stresses, number one, the largest one, or sigma 1, the most positive value, not the absolute value, but most positive value is what we by decree call sigma 1, and the most negative value, even though they might not actually be negative, but will be the other one. All right, so that's the differentiator between 1 and 2. You got to get the signs right as you set up your basic input stuff to go into these calculators, and then you have to back substitute ultimately to get to the place where you can orient those. And again, it'll be way easier to learn more circle to do this, and that's one of the things that we'll be doing next.